webinar on this particular topic, and we've got a very special guest today, Chief Joe Starnes. I was fortunate enough and blessed to meet him at Kill the Flashover Project in Columbia, South Carolina at the State Fire College there, where we actually did some live burns. It was very eye-opening for me especially in studying the NIST reports and the UL studies, FDNY Governor's Island studies, and many others. It's very rewarding to be around a subject matter expert and actually see the results in action. So we're going to talk quite a bit about some of Chief Starnes' work and then demonstrate some of that work via simulations and hopefully generate some interest along the way. At the bottom of the first slide here, you'll see the contact information for Chief Starnes and myself. Please don't hesitate to contact either one of us. You can also check out Joe's website at joestarnes.com or killtheflashover.com. So without any further ado, we'll just move on to topic of the day. That was a mistake on my part. Bear with me. I just lost my slide for a moment. I got a little trigger happy there. There we go. So this is what we want to discuss today is, first of all, why the Chief is out there doing what he does, why the research. Bear with me just one moment here. I've got a little connection problem. But I think anytime we do in a learning environment is first identifying why. So why do we need Kill the Flashover? Why do we need the UL studies? Why are they so important? And so we'll discuss some of those matters, and particularly how they're important to firefighters. I know Joe's passion and mine and Jonathan's as well is about making sure firefighters get home safely every night. Then we'll talk about some ventilation-controlled fires, why ventilation is so important today, particularly as it relates to today's fuels. With the high-surface, low-mass products that we see in every fire today, fires are getting hotter, quicker, and using more oxygen, and that's the key thing. It requires more air for these fuels to burn. And then we'll talk about the flow paths, and I'm going to turn that over to Chief Starnes because again he's an SME on the path and the flow of the fire. So, but the direction of flow is important, whether it's bidirectional, unidirectional, and then we'll talk a little bit about the neutral plane, and then how the pressures within the structure itself affects the fire, affects the firefighters, really affects all components of the incident. And lastly, but certainly not, or certainly equally as important as all, is the impact of door control. We've read the science, we've seen the literature, but until you actually are on a controlled burn with Chief Starnes and his group and see the impact, or you've tried it on your department, it's amazing. And just recently we had some firefighter losses with regard to wind-driven fires. So we know that if we can isolate our firefighters until we can make that mayday or that rescue, it's certainly going to be helpful. Size up is critical. One of the things that take-homes from South Carolina burns were make sure you're using that thermal imaging camera on size up. And so we'll talk a little bit about that. And then lastly, we'll dig into some simulations. So we'll start that off right away. So Jonathan, if you can switch me over to my sims, I'll just do one brief one, and then we're going to switch it over to Chief Starnes to go into more detail with regard to the simulation he's got ready for you today. And I hope this comes across okay. Now keep in mind that we've got we're working via the internet, so you might see some sluggishness with regard to the smoke and flame, but it'll give you an idea of you know, how to teach this and also practice with your crews and build the simulations accordingly. But obviously in the incipient phase of the fire, I'm going to get rid of this arrow key here in my menu. In the incipient phase, primarily what we're seeing there is, you know, obviously the fire and some smoke coming up, and it's mostly soot, and it's a matter of time before, you know, we get the right mixture, the heat, the fuel, and the oxygen before it makes that next change. Now, at this stage of the game, the fire is spread to all the furniture in the room. The room is basically fully involved. The temperature ceilings are about 1,400 degrees, and obviously, if we think about the integrity of our gear, particularly our mask and all of our PPE for that matter, it's a pretty dangerous environment here. As the fire exhausts itself from oxygen, you will see that temperature drop about 1,000 degrees. So we're now at about 500 degrees Fahrenheit, and you could effectively work in that atmosphere for a short period of time or duration with your current PPE. But from the time oxygen was introduced via the front door or ventilation of some type, within 80 seconds, that entire room flashes. And a short synopsis, if you will, of what Chief Starnes is doing is to help us prevent from getting into this 80-second window where we have our folks in that flashover environment. Again, if we go back to that previous slide, 500 degrees, we could probably effectively work within that environment for a short period of time. But once the flow path generates the sufficient O2 for the compartment that we're in, this is what's going to occur. So Jonathan, if you would, we'll switch over to Chief Starnes and let him talk about the flow paths.
First of all, thank you, Jim. I appreciate it very, very much. Jonathan, thank you very much. Let's see if I can make this work. All right. Did we get a screen?
Yes, sir.
All right. Which one do you want to do? You want to do it bidirectional first?
Yes, sir. I think that really gives a good example.
All right. We got to find a compartment. Basically, a bidirectional flow means that the firefighter was entering from this right side underneath the smoke. This is the most common approach, or from the unburned side, and then it creates this once the flow path develops. They're usually up under this column of smoke, and this bidirectional flow here is basically saying that the gases have to get out of the compartment and fresh air has to get in the compartment to sustain combustion, and that's why it's called bidirectional. The neutral plane will be formed somewhere between these two areas, and that neutral plane will get, as this intensifies and gets in extreme behavior, this will start to spin. That's where we get our spinning smoke. And once we get that, we start to get the mix, and then we start to get all the ignition or flame contact ignition underneath this. There's several dangers here. We can take a couple examples. The bottom line is that we're getting air exhaust this way to the right, and we get fresh air from the right to the left. So the left to the right is exhaust. That's called the overpressure area, and the right to the left is intake air supporting, I'll see it southern there, intake air supporting the combustion. And this area back here is the storage area, which there is no flow path, and that is, we lovingly, John Taylor's work, called the plug. If we were to enter this from the unburned side, and this was the way we would go, then this, once in residential construction under about 2,500 square feet, we're going to see this change anywhere from about 15 seconds to about 120 seconds. It's going to look like this side over here. It's going to, fresh air is going to come in. It's going to start to lift this just a little. This is going to grow, push this back down, and that neutral plane is going to grow. You don't have but about you have less than 2 minutes of this lifting before it starts to come back down again. And once it comes all the way down and the turbulence in, you can get all ignition. Or if this neutral plane area makes it outside to a lean area and comes back and lights it off, then that will flash this whole hallway where you are. So your gear cannot stand 1,000 degrees plus for just about 7 seconds. Your mask will fail somewhere around 3 to 400 degrees. Once your mask fails, for whatever reason, it'll fail quicker if you wipe it or push it or pull air in or run out of air. A lot of reasons the mask will fail at different temperatures. Bottom line, you will pull that air into your lungs. The searing heat will kill you, or the toxins associated with what you're breathing will kill you. And usually it'll kill you in a couple breaths. Max. If you're lucky, you'll die in one, but not two. So that's a bidirectional flow. Jim, any questions about what we just said there? Did I lose Jim? Hello.
No, sir. I think you did a great job explaining it. I think the bidirectional flow is something that we get a lot of questions on, so that articulates it very well.
All right, let's do the unidirectional. If you're ready.
Looks good.
Unidirectional flow says that cold air is coming in and fire is using it for consumption to powerize, and then the exhaust is going out the other side. That's the unidirectional. This are other and what it boils down to is there's no fuel on the unit on this side of the fire. In this particular case, this particular example, there's no fuel on this side of the fire, just fresh air until there's nothing there to flash. So if you can get a stream into here, this will cause this to cool and subside, and it'll go from a fire growth mode to a fire decay mode. This side is typically what we see out the window. After a while, that will, if it gets a sufficient flow, that will auto ignite out the window, and it will burn like a candle burns at the face of the window towards the fire. So if this was the candle, this would be the distance between the fire is to the window, and then once it leaves the window and reaches ideal mixture, you'll see fire flame steam from there. I don't hear you, so okay. This is the plug.
Hi.
Talked about it a little bit ago.
Sorry, Chief. It's Jonathan Kay. I think we maybe for other people as well here. We lost a bit of the audio in the last, I would say, 20 seconds or so. So it seems like maybe with the it's a good idea just check in if there's some important point that you want to make sure people have heard there. But I think maybe it's running also the program.
And that's kind of what I was doing. I was asking you guys if you had heard it, and I didn't get anything back. So undoubtedly that's the part we missed. Thank you. Are there questions, I guess, Jim?
Yeah, well, we're getting a little bit of weak video, correction, a little bit of weak audio, but I think you're understandable now. With regard to that bidirectional flow, or the last one you just mentioned, on the exhaust side of the structure with the auto-igniting black turbulent smoke, that's, as I understand what you're saying, that's most likely going to be the source of your heat signature on your 360.
Right. When you come out, this is going to exhaust out the window. The odds are, if this is a vent, we've been talking about vent-limited fires, not fuel-limited fires. In other words, this fire is producing more fuel than it has air to consume the fuel. So that's a vent-limited fire. A fuel-limited fire is a fire that has enough, sufficient, or more air than it needs to support all the fuel that's burning. So those are the two. But these two scenarios we've talked about have been vent-limited fire, traditionally what we find in a residential structure. And so from the standpoint of what we see outside is we may see a column of smoke, different colors. We may see smoke mixed with flame, or we may see a solid flame outflow from that window or that orifice wherever we are looking into. But the content of that fire is based on the richness behind that window. If that is too rich to burn, it's going to exhaust to that window, and then once it reaches an ideal mixture, it's going to flame it and auto ignite. If the flames ride like you have here in the simulation, if the flame rides the neutral plane underneath it, and that flame reaches the outside, it's the same thing as a striker to a blowtorch. You're just putting flame to that fuel, and when it's the ideal mixture, it'll burn. If you're used to a settling tank, you can make that too rich or too lean by the variation of oxygen and fuel. If you vary the oxygen enough to supply enough oxygen, that torch will burn it at its hottest temperature. Same thing goes here, except it's being regulated by the flow path and the pressure in the structure. The most common misunderstanding of all this is simply we're dealing with pressures. So venting, in my mind, this is a Joe statement, venting in my mind is a method of overpressure relief. The American Fire Service has used it to be optically sighted. We are normally, the way we fought fire for years, we have been thermally what I call blind, because we don't use the TIC, the thermal imager, in the tactical operation mode, in other words, fighting fire. So if you want to, we'll get into some of that in a second. But bottom line is, when we do a 360, we have two views. We have an optical view and we have a thermal view. We can be thermally blind if we don't take the TIC with us, so we don't see some of the thermal information. The thermal information tells us more about the fire dynamics than gives us the fine information for fire dynamics than the optical view does. We know color of smoke, we know speed, velocity is important, we know position of smoke is important, we know how the smoke is churning or not churning. All those are optical things that we need to understand. The thermal view of that is quite a bit different. One of the things I've often said, Chief, is as firefighters, we're scared of the dark. So on the plug side of something, when we're looking at it, if I would go back to the plug, let's do the plug a second. So I look at the plug, and I'm in this plug. I don't see anything unless I have thermal vision. What I see optically is just a black screen in front of my face, in my face piece. So if I have a thermal vision of that, then I can see this. And there's a lot of implications about how that dynamic's working. What I tried to illustrate in the plug is simply the plug builds a thermal wall down low, and the heat and gases reinforce and replenish the heat in the plug by going to the top of the ceiling and going out. That turbulence causes fresh air or oxygen back into the bottom side. This middle is a thermal wall. There's not a lot happening between the plug and the fire in the middle of this. And as it grows, and once it flashes, this will break down and all this will explode at one time. When you light off, if you can keep this fuel from coming into play in your firefight, you're a much safer firefighter. I don't know how that came across, but that's the reason understanding smoke storage is so critical. Chief, Jim, can you tell me if that made sense or not?
It does make sense, Chief, and you know, as you recall some of the discussions we had, and kudos to you for putting together a team of world-renowned scientists at the Kill the Flashover project. But as you recall, a few times the word depends came up, if you remember. So with a fire like this, obviously what I'm getting from you is take your thermal imaging camera, get your heat signature, but you also want to pay attention to the cold air as well, what it's doing. And then lastly, with this particular sim you have up now, there's always that debate, do I hit it from the burn side or the unburned side?
Yeah, and what we say is you don't want to be in this compartment in any way, shape, or form until you bring this down to the specifications of your gear. In other words, a stream that enters this compartment from somewhere else and kills this extreme temperature that your gear will not stand in this compartment, then you or your crew should not be in here, period. We're crawling up under, like on the right side here, we're crawling up under that and getting, sometimes waiting to flow our stream. We're not even killing this gas and fuel here, we're just going up under it. That is extremely dangerous. That's what's hurting us. So if we bring this down below, and the other thing is what happens in physics at 500 degrees. At 500 degrees, the molecular speed of all this process here changes tremendously. We go from, and 500 is not a number that we ought to write down and say that's the key number, because it's more than that. But the bottom line is, at 500 degrees, this speed of this, we go from 0 to from ambient temperature to 500 degrees a minute, we go from 500 to plus flashover over 1100 degrees in seconds. So we must keep this temperature from rising that way, and we must slow fire growth. We need to be killing fire growth before we make access to a compartment, trying to get to another compartment that is the fire compartment. I hope that made sense. So.
Now, with regard to the temperatures that you're talking about here, and obviously that's, like you said, an atmosphere or a compartment that we do not want to be in. With regard to the protection gear that we have today, on your department, do you have a go, no-go temperature reading on your tick?
We have a no-go, no-go condition, not a temperature.
Okay.
If you've got a neutral plane that's greater than 50% of the opening of the orifice, it's a no-go even if the temperature is low. That neutral plane means that's where the ignition is going to take place, where the first turbine is going to take place. So if I'm looking at a door and it's halfway down that door casing, even if I'm dealing with 350, 400 degrees, what I see as a profile picture, not what I'm seeing on the spot. Most cameras will give you a reflection on the spot. They'll give you a number on the bottom right-hand corner of the screen. What we don't want to do is use that spot to make a decision on our thermals. We want to make the thermals from the profile, the saturation of the screen of what we see on the camera. And we have to know enough about our camera to understand when if we have color camera, we have colors, or we don't have, we have grayscale. We have to know enough about our camera to understand that. So if I put for instance, in KTF on the burn building, if I put the spot on the outside away from the orifice where the flames are coming out, I'm going to see a temperature under a couple hundred degrees. But if I take the spot and move to where the flame is, I'm going to see it jump to 1200 degrees, and I'm going to see a temperature greater than 1000. My point is, what the profile is important. When I look at that camera and I look at the screen, I see a sunburst of saturation of the resolution of that camera. And when I see that, if I see temperatures greater than 500 in that sunburst, that's an indication I need to be looking for flow path, where the air coming from, how fast is it growing. The neutral plane, if I spot the neutral plane where the smoke is coming down on a door case, I make a 6-point check and I come back to that case and just benchmark it again. And if it's moved 6 inches hotter downward, then I need to change that before I move. Because the time I get my hose line and move in that compartment, if it moves 6 inches in 5 seconds, the time I do 30 seconds, I'm liable to have flashover conditions. I've seen it change from 400 and something degrees to flashover in about 18 seconds. So you've got to understand where the go, no-go is all based on the fire growth determination you can make, and temperature is one of the greater aspects of that. You've got to understand your instruments to do that.
And that was the purpose of my question, to really make it clear to folks that will be listening, that there seems to be this thought process that with regard to the thermal imaging camera, the go, no-go is based solely on temperature as opposed to, as you mentioned earlier, the profile, and then how quickly a 300-degree fire can flash over in today's fuels.
Yeah. To zero. What I want is that needle to be towards decay before I want to keep it on the decay side as I move to that compartment, to the actual fire compartment where I'm going to extinguish the fire when I'm doing the vent limited fire.
This is Jonathan K.
Those things are absolutely critical.
Could you just repeat the last? Sorry, I didn't hear that. It sounded important, and about 20 seconds ago, just the answer to that question. Just heard the tail end of it.
Okay, I'm not sure. Jim, where would you start there?
Well, we were talking about the go, no-go with regard to thermal imaging only, and you were talking about the overall profile of the fire as it relates to vent and how quickly this could flash over, even from a temperature as low as 300 degrees.
Yeah, I have a slide I can show you that shows 12 seconds worth of difference. 12 seconds. But if you move the camera, you take the spot, you take the profile, and you do something else, and you come back 12 seconds later, it's what happened in that room. if you were in that compartment, 12 seconds later, you would probably die without oxygen.
Yeah, and that goes back to the previous sim that we had on the 80-second simulation from the time oxygen was introduced into that compartment was a recreation of an actual event.
Right. That number, that's the reason I say that the go no go is still like it used to be. It is a question of skill judgment. If you look at that, but the judgment has to understand if you're in a growth mode. If you're in a growth mode, you may have arrived at that portal to enter that to access that fire at the low end of that growth mode. If you got a high growth rate, by the time you get ready, or a case where a firefighter called me a year ago and got burned and said basically that two of the firefighters had to go back outside, right outside the door, and fix their face piece to come back in. And the time that occurred, they stopped flowing. They developed a flow path from the garage to the kitchen, and then they ended up in the hospital with severe burn. It depends on the heat release rate of the fuel and the amount of fuel. The only thing we've done is reacted to the heat release rate of the fuel. The fuel is a big question. We wouldn't be having these conversations with our tactics if the fuel wasn't threatening us. And that's what's going on now. The speed of change is 10, in my calculations, when I entered the fire service in 1977, my tactics would have to be 10x faster to meet the fuel rate speed today. I've got to be 10 times quicker to do any tactic I do if I'm going to match the fuel rates plus the adding air. So if you don't manage air and you don't know it, you don't have a thermal vision as well as an optical vision, you're impaired to make the judgments you need to make on some of these accesses, some of these fires. And the wind-driven fires just exaggerate that so that we talk about it. The wind-driven fire is just a high-speed dynamic of what we've got going on in the fire anyway. And then the whole dynamics of wind blowing past a wall and creating an eddy and creating a low pressure. When we create a low pressure, fire's coming there, folks, if we're in it, and it's got air. If there's oxygen there and it's a low pressure, it's coming there. And if it's not, it's going to fill it up with fuel and not burn. Either case, it can be, and then the problems we haven't even talked about going from then limited fires and fighting in that direction as opposed to the way we open up fires today. The most fire departments today find the fire simply by adding air, and when the flame's out and says, hey, here I am, they fight fire. That is an extremely dangerous way to find the fire. I'll pause here, Chief, and you Jim, tell me what you think, what we need to do here. Because you know me, I can talk for a long time, Jim.
No, that's fine. One of the big take-homes for me, in addition to the great work you're doing with Kill the Flashover, is that most of our reports are coming from line-of-duty deaths as opposed to reporting every thermal insult on a firefighter. I'm sorry, say again. I lost that point. The point you were making that most of our reporting is from line-of-duty deaths, unfortunately, but we're not doing a good job of reporting all thermal insults on firefighters. Exactly. But we don't report burns, and burns are the defects, and the fatalities and the injuries are the defective. Okay, so we've seen it, what goes on inside the structure, and we get a little idea now of the flow paths. So let's take this outside the structure, if you will, and ranch-style home. And as we do our 360, you want to take your slide. I'm assuming you're showing your slide, right? Yes, sir. Do you not have it?
Yeah, the Charlie side of it, the Bravo side. Is that the one?
Okay, so we're right on the alpha side. That's what we have going on. You mentioned that auto-igniting black turbulent smoke coming out, obviously the flames, and unfortunately we sometimes focus too much on the flames themselves. Here's our Charlie side, and then we'll quickly move over to the Delta side of the structure. On arrival, and this goes back to the importance you talked about of our 360s. On arrival, it looked like a duplex, but we see we got 4 meters there, so we actually have a quadruplex. And coincidentally enough, no doors. So the value of taking that thermal imaging camera, getting our thermal readings, doing our 360. I love the term that someone coined in South Carolina, tactical patience, with regard to your 360. So anything you want to add to what you might see, do, or particularly tactically what you may do with regard to this size of?
Well, the tactical patient, I think, was in John Dixon's point. There's an NIST study that was done in Chicago, and there's an open window on the second floor. Like looking at this, you wouldn't know if there was an active plug or an active fire in the second floor of that. Looking at those windows, you wouldn't know for sure of what the condition was with that particular one, unless you were looking at it thermally. So if you're only looking at it optically, you don't know that you've got heat behind that. And what happens in that particular test is the fireman opens the front door, and you're familiar with that video probably. He opens up the front door, and then that window on the second floor starts to overpressure and starts exhaust is obviously coming out of it. So now we know we got extension from the first floor to the second floor for that fire, and that second floor is full of fuel, and it's overpressure and that fuel out that window. If you honestly would do that if you didn't look at it with a tick. And we're thermally blind if we don't look at it through thermal eyes. Thermal imager is the thermal eye. So when we walk around a structure, we get a good contrast, even though heat doesn't. A tick cannot look through a window, but a tick can see heat. If I'm 100 degrees hotter in one spot than I am the rest of the side of that structure, then why am I that hot? Is it a sun condition? Is it a false positive? Or am I actually getting heat from the fire? Typically what we will see is heat and heat leakage and seepage, especially as the fire starts to burn through channels around windows. We'll start to get a definition of what the heat is. In this case, on the Charlie side of this structure, you got smoke showing on that side. You could have heat and no smoke showing there, Jim, and the only way you're going to pick it up is with a tick. Your eyes it's like a dog and smell. You become super sensitive to things you can't see. So the bottom line is the thermal imager helps us locate and define. Also, the thermal imager is great for definition. When we heavy smoke, we see definition or contrast of pieces of fuel that are taking on heat but haven't got to the hot as the fire condition is. So that contrast is important. The fact that it does contrast is important with a thermal imager, and that gets into tick usage and whether or not things are contrasting. As what's in there heated up to the they call it whiteout in some cases, where everything in the room is the same temperature, and sometimes that could even be a body, unfortunately. But the bottom line is the tick is a set of thermal eyes, and if we do the 360, getting a good thermal view versus an optical view is great. And the last thing we've taught is simply that let your optics tell you that you need to verify it thermally, and then your optical vision says, I see something that's a clue, and then take a look at it with a tick to validate or invalidate your data that you need. It's just another data source, but it's a tremendous data source. If we're in the heat business, then why not take some type of thermal detector? And I'll put it there.
I agree totally. Now, with regard to the 360 and the thermal imaging camera, and obviously if we did the 360, I'm going to do it very quickly on this building again, and we're not using the thermal imaging camera, and time's gone by, let's go back 10, 15 years, and many departments today still are saying the alpha side of the structure, the front door, is the one I'm going in. Now, with regard to the fire flow sims that you showed earlier, let's assume that's going on inside on the first floor on the Charlie side. What is going to happen when we go through this front door, if that's something our department always does?
At some point, you will connect that pathway to air to that combustible fire. That's where you're headed. You're headed to the fire compartment. True, that's what our intents are. So if we create a flow path to that fire compartment, then at some point the fire will use that flow path. And once it starts to use that flow path, it will increase that fire. Because now it's like, again, it's a settling torch. What happens is when I take a settling torch, it's burning too rich, and I add oxygen to it. What does it do? It burns cleaner and brighter and hotter, doesn't it? And that's what's going on here. Once I leave that door open. Now, if I manage that door by keeping that door closed or have somebody to do door management and door control in some of the videos, we've tested the curtain at that point. We typically will 3D that door, wet that door with a solution or an enhanced stream, check it with a tick, open it, check it with a tick, hang a curtain, again, shut that door, hang a curtain in there so that when we next step is to throw that door open, and once that door is open, that curtain's doing what we needed the door to do. Now we got a really easy access into that compartment. That's the first go, no-go for us, is simply from the yard looking and going past that door. Let's say the door to the fire room is closed, and if the door to the fire room is closed, at that point, then what I'm going to see is lazy, detached smoke inside that compartment. That's another way of determining what I've got. I'll manage that smoke if I need the condition on my way to the pathway to that room. Then I'll treat the room, the compartment fire, just like the front door if I was at a fire behind the front door. I'm going to cool that area. I'm going to crack that. I'm going to put some steam, some enhanced steam into that thing. I'm going to control, bring that heat down. I'm going to get that. Once I get that heat down, I'm going to slide that door open. And
you know, we hear you loud and clear, and I was blessed enough to see it firsthand. 2 points here. Number one, opening that front door, will you agree, and leaving it open, if you would always attack from the A side of the building, is going to bring the fire to you at worst, and sorry, at best, and at worst, cause a flash up.
Yeah, it's anywhere you give, if you create a flow path, it's not if, it's when that fire's coming down that flow path.
Okay. The other takeaway, again, and Dr. K, I don't want to put you on a spot, but in the future, we're going to be able to add, like when you add victims to your sims, you'll be able to add a picture. And I heard you loud and clear and saw it firsthand, the use of fire curtains. So that's something that we'll have down the road. I can't promise you when, but at some time in the future, we'll be able to actually open that door, show the results, and then show the results via simulation after a curtain is in place. Do you see value in that, Chief?
What was your question? I got everything but the last part of the question.
The ability to add a curtain. So we'll open the door and then have the ability to add a curtain to simulations.
Yeah, right. We need to do that. And I think curtain will be in our future within the next 10 years. It'll be part of our choices on the fire ground.
Well, after what I saw, I certainly hope so.
Yeah. What we're talking about is air management. And the more we learn to understand that we're managing air like we're managing cool, which is the stream, we'll do better.
Okay, one of the things I did not show on this one here, kind of get a view of inside the structure, is you also have the ability to, you know, again, I doubt seriously you'd want a firefighter inside that compartment without controlling your vent, cooling the gases, etc. We have the ability to change the opacity on the firefighter to make it look like a view through a thermal imaging camera. So the thermal imaging camera views are also, you know, very much a part of what we're able to do.
Yeah, and I think
one more up here.
Yeah, I think that's critical, Jim. I think one of the ahas for most is literally watching the cameras that are fixed that we do. I lost you.
Okay, we basically did a 360. We're on the Charlie side now, and I think again it just articulates or demonstrates what you articulated earlier with regard to that flow path and you know where the flow path is.
You got a strong overpressure there coming out the orifice that you have there, where the wind is broken all the way out or not. You got a strong overpressure, and you probably with that, you probably got air coming to that fire from somewhere else in the picture you demonstrated.
And that's the point I wanted to make, that this is getting air from someplace else. And if we go back to, and this is probably a poor example, but I did it on the fly. If you go back to the alpha side, you can barely see it, but that door is open.
Okay. Jim, I got to take just a quick break. We'll be right back.
Okay.
I apologize.
No problem whatsoever. Okay, so now we'll just take this to another simulation. And the key of today, or our primary goal today, was to demonstrate a couple of things. Number one, discuss the Kill the Flashover project and what's going on with regard to the UL studies, NIST studies, the great work of KTF. And then how do we take that and apply it? Well, obviously, one might say 1403 burns. And my personal, Jim Murphy's personal opinion is our NFPA 1403 standards as they exist today are really setting our people up for failure, because we really can't train in that environment with regard to the fire flow, and particularly with regard to the high surface, i.e. plastics in the home, are going to burn at a greater heat release rate. So in my view, and that of many of my colleagues around the country and thousands of our customers, is that we can demonstrate this fine work that these folks are doing via simulation and get people to really understand the physics and the science behind fire, because that hasn't changed. The fuels have changed. Some of our tactics and strategy has changed, but the physics hasn't. And so if we can use simulations to teach that, we're now, one of the things that the Chief mentioned was always doing a 360 on a fire and using that tactical patience, using a thermoimaging camera as you do this. This is a recreation of an event. It wasn't this particular building or school, but it was an event that in fact did occur, where a rapid 360 was done of the structure. I mean, obviously, we know we've got a significant fire on the delta side of the structure, and then we go back to the alpha side and see the same view. Now let's go back to the delta side with a little tactical patience and the use of either a thermoimaging or just taking your time and get a closer view rather than being out here doing your 360, being in a little closer. This actually occurred where this was seen a few, maybe a minute or so into the fire. So we had victims that were obstructed by the smoke and the fire. So the key point with this simulation here, obviously, is to understand where the fire is, where it's going, how long it will take to get there, etc. But using that tactical patience on size up, and again, I have to credit, I believe it was John Dixon that discussed that at KTF. So with that in mind, let me see what else we have here for you today.
Yeah, I'm back too. I'm sorry about that.
Chief, I was just doing a 360, and we were talking about.
I saw that. I'm up with you. I'm up to speak.
Okay, so you caught the part about the tactical patience, and then this was an actual event where we got into a hurry and missed this because they were way out here doing a 360. So it was just, again, I was driving home the point of the importance of doing your 360s. Okay, so with that in mind, that's essentially what I have with regard to simulations for today. If anyone has any questions for Chief Starnes or Dr. K with regard to simulations, where we are, where we're going in the future, feel free to ask them now. The most important take-home for me with regard to simulations is I've been using them for over 10 years now to teach everything from Incident Command School at Orange County Fire to Tactics and Strategy, and now I'm kind of pimping out Joe's work in that I'm learning more about the fire science and how to apply it to simulations to teach with. So with that being said, that's all I have for today. Chief Starnes, I can't thank you enough for participating, and if you have any closing remarks or any add-ons to what we've discussed so far, I would love to hear them. And Dr. K, you may want to discuss anything with regard to SimsUshare and what the future of it is.
Dr. K, you want me to try this first, or you want us to do it first?
Oh, please, Chief, if you would go first, that'd be great.
All right. Well, one of the things that Jim and Jonathan has shown me is the value of this, both to teach post-event and for new firefighters pre-event. And then we had a discussion about taking the thermals and adding the thermal view to the simulations and how important that would be. One of the things we did is I show a picture of a fire room and I say guess the temperature. And when you do that without the thermals, you have a hard time of guessing the temperature. So I think, Jim and Jonathan, the work you're doing is critical. I am a big advocate of what you do, and I'm a big advocate of getting it in as part of the standing critique of how we critique fires. Because I think the greatest change for fire service is simply to improve our critique thermal. If we do that, we'll have a better discussion. So thank you both for all you're doing, all your hard work.
Thank you, Chief. I can't say enough good things about you and your team and the work you're doing.
Yeah, and so this is Jonathan, and certainly it's really our honor to have you. And I know in discussing this, as much as we like to take credit for what we're doing, we know at the end of the day it's really what people do with the tool and how they're using it instructionally. What Jim is doing, what you're doing, Chief, is really what makes it relevant and important to students. So appreciate your kind words, but I really want to let you know how important what you're doing, anything that we can help in making it more relevant and more useful to what you're teaching. We certainly are very welcome to hearing suggestions. It looks like we have one person, Tim. I don't know if you want to chime in any kind of questions or thoughts or feedback before we close the meeting.
I think you guys did a good job. I work here at the Fire Academy in New Hampshire. We do a lot of exam simulation stuff, and this will help us. I'd be interested from Chief Starnes how we could simulate better the slower 360 with using thermal imaging.
Now, this is Jim. If I can chime in, Chief's got some good images, but you can really take an image from a thermal image camera and use it like the background photo you're seeing now. So you could have a room that was on fire. You could get your signature readings from your camera, photograph it, use the navigational buttons to navigate to the background of that photo and show the actual signature readings.
You know, one time can add, Jim, one of the most powerful things KTF has been every shot. We always video thermally and optically the fire room, every access path, and not every plug, but we have a tripod in the access path, a tripod in the fire room, and a tripod in the storage room, and they have an optical camera and a thermal view. And when you do that, you let the firefighters understand what they're seeing both ways, and that's a big deal because the thermal data is a whole lot more risky than the optical data. It will go, if the risk, if it just with your eyes doesn't look as great as it is if you look at it thermally. and to understand how to manage that risk and where the cold air is coming from is critical. So to your point, simulations would be a great way to compare quickly what we're seeing and insert how we're making our decisions and what we're trying to manage to do that, especially in rescues. I think it's critical in rescues. I think the number one place to improve in our ability to do rescues, both for a customer and for our own RIT in this case, is simply to have an IAP that includes the thermal control as we try to get to the customer or to the firefighter. That's it.
Well, Chief, I agree. We're at that 50-minute mark now, and once again, I cannot thank you enough for your generosity and your time and the work that you're doing. And you know, much like, unfortunately, the reason you do what you do is because of the thermal insult to firefighters and the line of duty deaths. Unfortunately, that's the reason you're passionate about what you do. Dr. K and I are passionate about what we do because of your work. We want simulations to be out there as part of that driving force to make sure everyone goes home safely. So having said that, we're going to call this one a wrap, and thank everyone for participating, and look forward to the next one.